After the previous rather large video, I want to make something that's very short but will have some relevance to us and also point out something that's often misunderstood. The usual units of measurement, which I'll call the MKS system, use meters, kilograms, and seconds for our measurements. In some applications, it's convenient to measure distances in light years and time in years. The speed of light in those units is 1 light year per year. The value is 1, but it still has units associated with it. What's often done in both special and general relativity is to change the unit of time. I'm thinking of time as being along an axis, just as the x, y, and z are. So if I measure x, y, and z, say in terms of meters, if you want to be fair about it, I should measure time in meters as well. 1 meter of time is the amount of time that it takes for a light ray to travel 1 meter. Since it takes 1 meter of time to travel 1 meter of distance, the speed of light is 1 meter of distance divided by 1 meter of time, which is 1. But more importantly, meters over meters cancels out. The C is dimensionless. It's 1, not 1 and then some units, just 1. This is like radian measure. If I write that a speed is 0.8, then I mean that some object is traveling in a way that it moves 0.8 of a meter of distance per meter of time. Speeds are dimensionless now as well. In the Lorentz boost, in the positive x direction, the gamma is 1 over radical 1 minus v squared. V is dimensionless, v squared is dimensionless, this 1 is dimensionless as well. If you look at the two formulas for the Lorentz boost, though, if gamma is very close to 1, if the speed is small compared to the speed of light, then this reduces down to essentially x bar equals x minus vt. This is what Isaac Newton and Galileo would have predicted. That first formula is more troubling, though. The second equation is what you would expect from classical mechanics. It says that the value of x bar changes as t changes, even if the x doesn't. What's not Newtonian or Galilean, though, is that formula. This says that the t bar values are going to be a mixture of x and t in a way that is similar to how x bar is a mixture of x and v. At this point, a person ought to be strenuously protesting. When the speed is very small compared to the speed of light, Newtonian physics works pretty well. We don't see that time is not an absolute thing. So what's happened here? Why don't we see that? And under what circumstances might we see it? Again, in these c equal 1 units, the gamma, which is the reciprocal of radical 1 minus v squared, under the radical, this is dimensionless, and so is that. How can I revert back to meter, kilogram, second units? This, I'm just going to leave as 1 because it's dimensionless. This, I have to write down something that represents the fraction of the speed of light that we're moving, and yet is dimensionless. And then we have to square that. That's not very hard to do, though, so we'll just write things down. Let's think about the x bar formula. I already know how to fix up the gamma. It's the reciprocal of this quantity. What about the stuff inside the parentheses? If I think about what that would look like in MKS units, x will be in meters, v will no longer be dimensionless, it'll be in meters per second. Time will no longer be in meters, it'll be in seconds. So x minus vt in ordinary units already has the units of meters minus meters per second times second. The quantity inside the parentheses already has units of meters. So I can just leave that formula alone. How about the time equation? I'll have seconds in meter kilogram second units minus speed, which will be in meters per second. So there's the V times meters. One term has units of seconds, which is what we want, and the other one doesn't. It has units meters squared per second. The standard idea is if I was working in the C equal 1 units, if I felt like it, I could slap down a factor of C or C squared or C cubed anywhere I like. So what I'll do is I'll put in 2 factors of C in the denominator. If I'm using the usual units, then I'm just going to get the correct units out. If I'm using my special relativity units, I'm just dividing by 1 squared, so it doesn't make any difference. So in my formula for T bar, I'll write gamma as 1 over that quantity. T already has units of seconds in the ordinary units, minus Vx, I'll divide by C squared by 1 squared in the special units, and then I'll remember what the speed of light is in meter kilogram second units. So to summarize, T bar is going to be gamma multiplied by T minus V over C squared x. Gamma is this quantity. X bar is gamma times x minus Vt, and we are now talking meters, kilograms, and seconds again. Let's suppose that the speed was small compared to the speed of light, small enough that I can't distinguish the gamma from being 1. That doesn't mean that I can ignore this term because I can make the x real big. Under our current assumptions, v is small compared to the speed of light, so v over c is small. C's 3 times 10 to the 8 meters per second, so v over c squared is microscopic. Even so, if x is big enough, then this second term will be significant compared to the first one, and you'll see odd mixtures of space and time, just like you do when you're moving close to the speed of light. So the weirdness is not altogether due to this factor. If we could directly experience very, very large distance scales as individual people, we would notice that time acts as oddly as the x bar coordinate does. It's a matter of scale. This goes back to the comment about we don't know Jack. So let's suppose that you had some incident that corresponded to t equal 10 seconds. Suppose you had another inertial reference frame moving at 1 meter per second relative to the first. How big does x have to be before you'll start noticing the time is all messed up? So how big do I need to make x in order to make the second term roughly the same as t, because then there would be no missing this kind of effect. Direct calculation says x would need to be about 9 times 10 to the 17 power meters. If I've done my unit conversions correctly, this works out to be roughly 93 light years. If we had direct personal experiences with chunks of space that were on, say, the order of 100 light years, this relativity effect stuff would be in our face, even though we might not be moving very fast at all relative to the first inertial frame. Things actually are considerably weirder than you might think. In an upcoming video, I'm going to look at the situation where an individual experiences constant acceleration. For that problem, it'll be convenient for me to use years and light years as my units of distance. I'd like to figure out what an acceleration of 1 light year per year squared amounts to. As I recall, there are about 6 trillion miles in a light year. Each mile contains 1,609 meters. A year has about 31 million seconds in it, so 1 light year per year squared is going to be that number of meters by that number of seconds squared. In an extremely weird coincidence, if you figure out what this is, it works out to be just a little over 10 meters per second squared, which weirdly is very close to 9.8 meters per second squared, which is the acceleration due to gravity at the surface of the Earth. As far as I know, this fact that these numbers are so close together is a total coincidence. Later, when I want to have an experiment where some individual is accelerating at roughly 1g, roughly 9.8 meters per second squared, I'm going to call it close enough to say 10.045 meters per second squared, which, using years and light years, mean that the acceleration is 1. That'll be very convenient for us. This is an extremely weird coincidence, though, but as I said, as far as I know, there's no deep meaning there. It's just a coincidence. I wanted to keep this video short, talk about units, make this comment, and then we'll talk more about stuff in the next video. I hope everybody's having a good day, and I'll talk to you again soon.